We're in Chapter 3, Section 3.1, where we will be looking at several measures of center. Most of which you've probably heard before, but we're going to formally define. The arithmetic mean of a set of numbers, right? We're going to assume that they're called x1 through xn, is, well, you've probably heard of it, you add them all up and then divide by the number, right? Now, I'm going to write it like this. X bar equals x1 plus x2 plus etc. plus xn divided by little n, and then I'm going to write the Greek letter mu equals x1 plus blah 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 plus x, and we're going to call this capital N divided by capital N. It's the same thing, but I just want to point out, why do we have both of them? Because x bar is the sample arithmetic mean, and mu is the population arithmetic mean, right? So Greek letters for population, English letters for sample. Now, we often refer to the arithmetic mean as just the mean, or you've also heard this term, I'm sure, the average, right? Now, how is the mean useful? Well, you can think of it two ways. I can think of it two ways in which you could think of it as the measure of center. If every value x1 through xn were replaced with x bar, then x bar would still be the same. Right? That's one way you could think about it. Maybe I'll just say one. Another way to think of it, and this is a little bit more technical but a little more visual, is that if you consider each value to be a certain distance away from the center, then the mean is that center, right? So if, for example, we have a number line, I don't know, maybe this is like 0, and then this is 10, and then this is, etc., right? We number our stuff out. And we have our various numbers here, maybe there's some numbers here, whatever. Maybe we've got some numbers clustered around here, I don't even know. But suppose we just have, some sort of a dot plot or something like that. Well, the measure of center is wherever we could place a fulcrum. If you imagine this like a seesaw, it's wherever we could place a fulcrum, and this seesaw would be perfectly balanced. My guess is it would be somewhere around here or something like that. So I'll say x bar perfectly balances, balances the numbers, or I should say the data, right? So it's not necessarily in the exact middle, right, it's clearly closer to the right, but it's still, how would I say it? It's still balancing it, right? Okay. So anyway, let's look at an example, right? Use Minitab to find the mean ERA of all qualified stars in 2025. Now, I went ahead and I went to fangraphs.com. I clicked on leaders, pitching 2025, and I came up with this screen. Okay? And then I copied and pasted it into Minitab. Okay? And then I went ahead and labeled the ERA column, right? So we know which one is which. Okay? So then what we can do is we can go to calculator. Actually, you know what? We don't even need to do all this. We can just go to basic stats, display descriptive statistics. Yeah, this will be easier. And then we can actually just scroll down until we say, oh, look, ERA. Thank goodness we labeled it. And then we go to statistics. We've got a bunch of stuff that's very useful, but we don't really care about it right now. So I'm going to uncheck everything except mean. And then look at that. It just spits out an answer. 3.82. Now, in baseball, I don't know if you know this, but ERA is rounded to the nearest hundredth, so that's what we'll do. We'll just say 3.82. So I'm going to say mu, maybe I'll use purple. Mu equals 3.82 is the mean ERA for qualified I should say MLB pitchers. In 2025, thus far, right? By the way, qualified just means that they've pitched enough innings, they've played enough time, so to speak. Is the mean ERA in the data set? Let's take a look. Let's go. I think we should be able to order this. I don't know if it's gonna let us do it like this. Maybe if we format the column. No, never mind. We can't do it that way. I'll just look at this really quickly. Data. I think it's under data. Sort. And we're going to sort column ERA. Select. Sure, let's do it increasing. Yeah, let's just do it at the end of the worksheet, right? Whatever. Oh, whoops. Here we go, ERA. So anyway, if we just go ahead and look, it's sort of a lot of other stuff, but anyway, if we look, we see no, there's no 3.82 in there. It's close, but not quite. No, mu is not in the data set. So, no, mu does not need to be in the data set. All right. Now, I just want to point out that we did use mu and not x bar because we did find the mean ERA of all pitchers, right? All qualified pitchers. I'm considering that my population. That was the population of interest, and I found data on every single one of them. Thank you, Fangraphs. So because of that, we get to use mu. For a sample mean, we use x bar. Right? We just want to use different notation because, again, as we've seen, there's a difference between statistics and parameters, between populations and samples, right? So why do we consider both population and sample means? As stated previously, we can't always collect data from an entire population. So we collect sample data we find x bar, our statistic, and then use x bar to estimate the true population mean. Okay? And then we'll get into this a bit later, chapters 8, 9, 10, 11, that kind of stuff. Okay. Now, let's move on to another measure of another measure of center. Again, I think you've probably heard of this one, but maybe not. It's called the median, which measures the middle value of a data set. Now, when I say, I mean like counting wise. Right, as in if you have a certain number of data points, the median is right in the middle, whatever that value is. Right, so find the median ERA of all ERAs. Well, this is a lot, so it'd be kind of tough to count the middle, but actually it wouldn't be that bad. I can actually do this one by hand because Minitab sorted this out for us. We have only 54 data points, I believe, right? 54 ERAs. So I'll just I'll formalize this in a second, but 54 divided by 2 is 27. So what we actually do is we take the average of these two ERAs, and that's going to be our median. All right. So we're going to get, I'm going to put this in the calculator. We're just going to say 4.35 plus 4.64. Whatever, I'll store it in some variable. I don't even care. Right there. Whatever. There. Is it 8 point? Oh, whoops, sorry. We need to divide that by 2. My mistake. Let's can we use parentheses? Yeah, parenthesis. Ooh, that would have been nice. Blast. Let's just do this. There we go. 4.495. Okay. And again, we'll just round to the nearest hundredth. So we'll say it's 4 point. Nah, well, whatever. We'll just keep it. So I will formalize this in a second about how exactly I got this. Which is not in the data set. Right, just to, right. Of course it wasn't in the data set, right? We took the middle too, and it wasn't in the middle. Right, so once again, no, the median does not have to be in the data set, although it can be. Okay? Now, how do you find the median? Well, in general, we do this. We order the data set, right? So if we have x1, etc., through xn, well, that implies that x1 is less than or equal to x2, is less than or equal to, etc., is less than or equal to xn, right? Lowest to highest, okay? Determine whether the data set has an even or odd number of data points. This matters. If the data has an even number of points, then the median is the mean of the values xn over 2 and xn over 2 plus 1. i.e., xn over 2 plus xn over 2 plus 1 divided by 2. Which is what I did here, right? I multiplied it by a half. That's the same thing as dividing it by 2, right? If the data set has an odd number of data points, it's actually a lot nicer. The median is just it's the middle value, which turns out to be the n plus first over 2 over second value. Right, so if there were 53 ERAs, it would have been the 27th data point. But because it was 54, we had to take the average of the 27th and 28th. Okay? So let's take a look at this. Cross out what you have in your notes and just do this instead, right? Find the median of this data set, right? So again, we have an even number, right? We have 1, 2, 3, 4, 5, 6, 7, 8. So the median is 15 plus 31 over 2. Right, do we see how we got that? Right, because this is 1, 2, 3, 4, 5, 6, 7, 8. You can just see, right, that the fourth and the fifth data points, like those are the middle. If you're not sure what the middle is, just divide 8 by 2, and you get 4. And so you just find the middle of those two, right, the average of those two. Right, and this is 46 over 2, and that is 23. Okay, so that's how you do it. So, comparing the mean and the median, what would we say? Well, a measure is resistant if it is not sensitive to, I would say, outlier values in the data set, right? You could say extreme values, right? The median is resistant. The mean is not. Okay? So sometimes you want the mean. Sometimes you want the median. Sometimes you don't want the data to be resistant. Sometimes you do. Why? Well, I'll leave that to you. Think about that for a minute. Now, lastly, and this is the most simplistic of them all. You may have also heard of this. The mode of a data set is the most, I should say not the most common, but the most frequent value. That's it. So how does the mode appear on a graph? Well, whatever shape your graph has, whether it's continuous or whatever. Actually, maybe something like this. It's the highest frequency. So it's just the highest point on the graph. Right? If multiple points or classes are tied for the highest frequency, then they're all the mode. If all classes, or I should say not all, if every is what I was going for here. If every class is the same frequency, then there is no mode, right? Because we don't want to say every single value is the mode, right? In fact, if that happens, then we have something called a uniform distribution, right? We have something like this. Imagine a histogram that looked like this. There we go, right? And you have like 1, 2, 3. Right, something like this, where everything is the exact same frequency. And that's all for this video.